Hello, my friends, and welcome to a new lecture about artificial intelligence. We already learned what are the different branches of AI, then we learned about problem solving by search, and in here we say that there are two kind of problem search algorithms, uninformed search and informed search. Then we studied the first algorithm like BFS, and now it's the time to learn about DFS, depth first search algorithm. So DFS, this is one of the fundamental graph traversal algorithm. DFS is a kind of recursive algorithm, and we use this algorithm to explore a tree or even a graph data structure. So in here, the process begins at the root node that you can see here as the root node here, and we follow each path as deep as possible before backtracking to explore other paths. So as you can see here, first we go to this one. In BFS, we go to the blue one, but in here we go to this one, right? Next, we go to this one, then we go to this one, then here, right? This is how DFS works. This is different by BFS. In BFS, we explore all nodes at one level before we go deeper. DFS is typically implemented using stack data structure, either explicitly or implicitly through recursion. This stack keeps track of the depth being explored, and also it allows the algorithm to backtrack efficiently when it reaches at a leaf node or dead node. We call this one as the leaf node. Although DFS and BFS, they share the same goal of traversing a graph, their strategy and memory requirements are very different. DFS dives deep along a branch, which usually results in lower memory usage compared to BFS. In BFS, we must store all nodes at the current level. Let's focus on the strategy and implementation of DFS. The main strategy of DFS is very simple. We always expand the deepest node first. In other words, it follows one path all the way down before considering other branches. This allows DFS to explore solutions that are far from the root efficiently. In terms of implementation, in here we use a fringe, and this fringe is a kind of LIFO structure, last in, first out. This stack keeps track of nodes that have been discovered but not yet fully explored. When a node is expanded, its children are pushed onto the stack, and the algorithm always picks the most recently added node to explore next. So you can see here, we are in S and we want to go to G, right? So this is the search tree. We start at the root or S, then we go to D. In BFS, we go to E, but in here we go to B. From B, we go to A. Then each time we check whether we reach the goal state or not. If not, we go to the C. In here, we check whether goal state or not. No, we can go to A. Then we go to E, E, H, H, P, P, Q. Then this Q, same, right? From H we can go to Q, from P we can go to Q. You can see here, from H we can go to Q, from P we can go to Q, right? Then from here we can go to R, then from F. Every time we check whether we are in G or not, because not, we go to C, we go to A, then here, and we finish it, right? This is how DFS works. Now, let's discuss the performance of DFS, this time in terms of solution depth path. First, regarding completeness, DFS is not guaranteed to find a solution in all cases, right? It may follow a very deep or infinite branch and miss a solution at a shallower depth. Regarding optimality, DFS is not guaranteed to find the least cost path because it explores a path to its deepest node without considering shortest path that may exist elsewhere. For time complexity, DFS may need to explore all nodes down to the solution depth of S. If we consider B as the branching factor, the number of nodes expands is roughly O of B in power of S. In case of space complexity, DFS is memory efficient. The number of nodes on the fringe is proportional to the current path length times the branching factor, so B multiplied S. If we consider B as the branching factor, that is the maximum number of successors that any state can have, and S is the maximum depth, right? Then we have solution at various depths, right? So node 1, here one node, but in here we go for B nodes, right? And B in power of 2 up to B in power of S for S tiers. So here the total number of nodes in the tree up to depth of S is B in power of S. So one node B in power of 2 up to B in power of S, then B or B of B power of S. This shows why DFS is very memory efficient compared to the BFS, while still potentially requiring exponentially many nodes expansion to reach a solution. Let's analyze what nodes DFS actually expands and its key properties. DFS typically expands some left prefix of the tree. It means it follows one path deeply before exploring alternatives. In the worst case, it could process the entire tree. So if the maximum solution depth is S, then the time required is P in power of S. Regarding the space usage, DFS is memory efficient because the fringe only needs to store the sibling along the path to the root, which gives a space complexity of B multiply S. So now we go for completeness. DFS is complete or not? Not necessarily. If the tree has infinite branches or cycles, DFS might never find a solution unless we explicitly prevent cycles. Finally, DFS is not optimal. It always finds the leftmost solution along the explored path. It does not consider the depth or cost of solution. So in summary, DFS is memory efficient and simple, but may require exponential time and does not guarantee completeness or optimality without additional precautions. So here we see how it works. From S, we go to, so at level 0, we go to S, then we go to level number 1. In level number 1, we go for A, not for H like BFS. Then from A, we go to B. Then again, we go to D, right? Because E is here, we go to E. Then we go to this one, C. Then we go for G and we finish it here. We do not go for the rest because G is a goal state. Let's now consider the advantage and disadvantage of DFS. One key advantage of DFS is that it requires very little memory, so less memory is an advantage. Unlike BFS, which must store all nodes at a given level, DFS only needs to maintain a stack of nodes along the path from the root to the current node. This makes it highly memory efficient. Additionally, if DFS happens to follow the correct path toward the goal, it can often reach the solution faster than BFS. However, DFS also has some disadvantages. Because DFS explores deeply along a single path, many states can recur. And there is no guarantee of finding a solution if the recycled or infinite branches exist. And also, DFS can potentially go into an infinite loop. How it can go to infinite loop if the search tree is very deep or unbounded and cycles are not properly handled. So in summary, DFS is memory efficient. It requires careful handling to avoid repeated states and infinite loops. Okay, that's all for DFS. Please feel free to ask me your questions if any. Thank you and see you in the next lecture.